Hello, welcome to another module in this massive open online course. So, we are looking at the least squares optimization problem, and we also derived the least squares solution, that is the solution to the least squares optimization problem. So, let us continue our discussion. So, we are looking at the least squares, which is a very important optimization problem. You can also think of this as an approximation or modeling problem. And what we have seen is that when we have an overdetermined system of equations, y bar equals a x bar with A being an m cross n matrix and m greater than n, this is overdetermined, correct, and therefore, to summarize, and this cannot be solved exactly, therefore, what we do is we minimize norm y bar minus a x bar square. This is termed as the least squares problem, and the solution to this, the least square solution, we have derived this previously, that is x hat equals A transpose A inverse A transpose into y bar. Okay. And now, if you look at now let us look at some aspects, salient aspects of this solution. Now, consider this matrix A transpose A inverse into A transpose. Okay. Now, consider the matrix A transpose A inverse into A transpose. Now, we can see that you can easily say that this size of this matrix, so A transpose is m cross n, A is m cross n, A transpose is n cross m. So, this is basically your n cross this is n cross m. A transpose is this is n, A transpose is n cross m. So, this is n cross m, this is m cross n. So, A transpose is n cross n and A transpose is n cross m, implies if you look at A transpose A inverse, that is therefore, A transpose A inverse into A transpose, this is, you can easily see this is an n cross m matrix, okay, m greater than n. So, this has more columns than rows. Okay. But the interesting thing here is, now if you look at A for m greater than n, non square matrix, this implies that A is not invertible. Okay. Now, we are considering a scenario in which m greater than n, which means the number of rows is much greater than the number of columns. So, A looks like this. So, this is also known as a tall matrix, that is the height, number of rows of the matrix is much larger than the number of columns. So, the matrix looks like a tall matrix. Now, for non square matrix obviously does not have inverse, but you can observe a very interesting aspect, that is, if you look at A transpose, if you look at this matrix A transpose A inverse into A transpose and you multiply, you take its product with A. Now, you look at this, so A, if m greater than m, it implies that it is not invertible, but if you look at this A transpose A inverse into A transpose, multiply this with A. Now, look at this, we have A transpose A inverse, we have A transpose A. So, this is basically your A transpose A inverse times A transpose A, which is identity. So it is as if, although A is not invertible, it is as if this matrix A transpose A inverse into A transpose, this matrix acts, is acting, is behaving, you can say, is behaving as an inverse of A, right. When you multiply it on the left with A, it is giving identity, alright. So it is behaving, it is not an inverse because A is not invertible when m is greater than n, but it is behaving as an inverse. This is therefore known as the pseudo inverse of A. Pseudo is, quantity is pseudo when it is not actually the quantity, but it gives the appearance of that quantity, okay. So that is basically termed as, so this quantity A transpose A inverse into A transpose, this is termed as the pseudo this is termed as pseudo inverse of A, and this also, remember, a left inverse, because it is only true when you multiply it on the left. This is also the left, not the, it is A left inverse of the matrix. Now to understand, explore this further, this nature, and to understand, to get some intuition behind this solution. So what we want to do is, we want to get some intuition behind the least square solution, and the intuition is very interesting. The intuition behind the least square solution. Now if you look at our problem, we have y bar equals a x bar, this is our problem, but we know that there does not exist any x bar, that is, this does not have any solution. So this is, does not have any solution, which implies that no matter what x bar you choose, it will not satisfy y bar equal to y bar equals a x bar, which means y bar minus a x bar will always be non-zero, that can be denoted by a vector e bar, alright. So there is no vector x bar because this is an overdetermined system, remember that is what we said, unless if you consider three equations and 2 variables, you have 3 lines, and unless they all intersect at a point, this does not have any solution. So there will always be an approximation error, let us denote that by e bar. So this is the approximation error. So this is the approximation error. Now therefore y bar minus a x bar equals e bar, this is the approximation error. Now let me write it a little explicitly. So this will be y bar minus A is an m cross n matrix, which means it has n columns. So these I can denote by a1 bar, a2 bar up to an bar times x1, x2 up to xn. So this is your matrix A and this is x bar. So these are the n columns of the matrix A. And so this is equal to e bar, and so this implies that y bar minus, now if you multiply this out, you will get a1 bar times x1 times a1 bar plus x2 times a2 bar. So this minus x1 times a1 bar plus x2 times a2 bar plus what xn times an bar, this is equal to e bar, the error vector. And now if you look at this, x1 times a1 bar, x plus x2 times a2 bar, so on until xn times n. Now this is nothing but a linear combination of the columns of matrix A. what this is this represents a linear combination of the columns of the matrix A. Okay. So, now you have this linear combination of the columns, which implies that this approximation, that is A times x bar, always lies in the subspace spanned by the columns of A. Remember, the linear combination, consider all the linear combinations of these columns, you get a subspace. So, which means therefore, this lies in the subspace therefore, this lies in the subspace spanned by columns of A. What you have over here now, to represent this pictorially, if you take let us say this plane, remember a subspace, a plane is nothing but a subspace. So, let us say you have the subspace which is spanned, just to give you an idea I am representing the subspace by a plane. So, let us say this is the subspace spanned by columns of A. Let us say this is subspace spanned by columns of A, and you have your vector y bar, which does not necessarily lie in the subspace, and you are trying to form an approximation which lies in this subspace. So, this is your approximation. Let us denote this approximation by y hat. This approximation, let us say this approximation is, let us say you denote this by y hat, and this approximation, and let us say or let me just, so this is your A2 bar, and this approximation is, let us say you denote this by y hat. Now, this y minus y hat, this is the, if you look at this is the corresponding error. Okay. So, this is your corresponding error vector. Okay. So, this is y minus y hat. Okay. This is your corresponding error, and therefore, now E bar equals y bar minus y hat, and what is this? This is the distance from y bar to the subspace, or you can say the plane that is spanned, plane or plane, let us make it simple, plane containing A1 bar, A2 bar up to. So, what you can think of this as, basically you have a vector y bar and you have this plane that contains y A1 bar, A2 bar, An bar, alright, and this plane contains different possible approximations y hat. Now, what is the error? Error is the distance between this vector y bar and y hat which lies in the plane, and we want to find the error, the vector error, I mean we want to minimize this error, that is we want to make the error vector E bar such that it has the minimum, or in other words the distance of y bar from this plane has to be minimum. And now you can see this error, which is the distance of y bar from this plane, is minimum when the error is perpendicular to the plane, that is the whole point. So, this error, which is nothing but the distance, geometrically you can see this error is minimum in E bar is perpendicular to the This is the important idea. So, this error vector is minimum when it is perpendicular to this subspace that is spanned by a1 bar, a2 bar up to an bar, or we can also say that this error vector is orthogonal to the subspace. This is a big idea. So, this E bar is orthogonal . And when is this orthogonal to the subspace? This implies that E bar has to be orthogonal to each of the vectors in the subspace. This means E bar has to be perpendicular to a1 bar, a2 bar up to an bar. So, E bar has to be perpendicular to the subspace, and we know the condition for orthogonality. The condition, the two vectors are orthogonal when their inner product is 0, which means we must have a1 bar transpose e1 bar equal to 0, a1 bar transpose or a1 bar transpose E bar, sorry, there is only E bar equal to 0, a2 bar transpose E bar equal to 0, so on an bar transpose E bar equal to 0. That is, E bar has to be orthogonal to all these vectors a1 bar, a2 bar up to an bar. And now you can write this, you can write this as a matrix. So, this implies basically, now you can concatenate these conditions as a matrix. So, this implies a1 bar transpose, a2 bar transpose, so on up to an bar transpose into E bar equal to 0, and this implies, well, this is nothing but, now you can see this is nothing but the matrix A transpose. So, this implies A transpose E bar equal to 0, but E bar is y bar minus Ax bar. So, this implies A transpose times y bar minus Ax bar equal to 0. This implies that now you observe something interesting, A transpose y bar equals A transpose A into x bar, which is a condition that we had already seen, which implies that x bar, or the best vector x bar that minimizes the error, that is x hat equals A transpose A inverse A transpose into y bar. Okay. So, this implies that x hat equals A transpose A inverse into A transpose into y bar. So, this implies this is nothing but, again you get the least square solution, which is basically exactly so intuitively what the least square solution is doing is basically finding the vector y hat, which is the best approximation to y bar, in the subspace that is spanned by the vectors a1 bar, a2 bar up to an bar, which are basically nothing but the columns of this matrix A. And therefore, what is this matrix? So, therefore which implies the error vector E bar, which is the distance of y bar to y hat, or basically distance of y bar to the plane, is minimum when the error vector is perpendicular to the plane, which implies that error vector has to be perpendicular to all the vectors a1 bar, a2 bar, an bar, which span the plane. Okay. Now, in addition, what is y hat? Now, we can see y hat, that is approximation to y hat is nothing but A times x hat, which is equal to A times A transpose A inverse A transpose into y. Now, what is y bar? Now what is y hat? Remember, y hat is the best approximation. Now, if you look at this plane again, let's go back and look at this plane again. This is your vector y bar, this is your vector y hat, and the error vector is orthogonal. and the resulting error vector is orthogonal. Okay. And therefore, what is y hat? Now, y hat you can see is the best approximation to y bar in the plane, or you can also say y hat is the projection of y bar in the plane or subspace containing. So, y hat equals projection, the best approximation in the subspace of y hat is the projection of y bar in the subspace or spanned by a1 bar, a2 bar, an bar, and this matrix which is giving you the projection. So, when you multiply this matrix by y bar, you get the projection. So, this implies that this matrix is the projection matrix. This implies that A into A transpose A inverse A transpose is the projection matrix. And the projection matrix for what? Projection matrix for the subspace that is spanned by a1 bar, a2 bar, an bar. That is it. So, this matrix, which is very interesting, this matrix which is the projection matrix that is spanned, this is basically given as A equals A transpose A inverse into A transpose. This is the projection matrix corresponding to the subspace that is spanned by the columns of the matrix A. Okay, so, this is basically your projection matrix, and this you can see this this has very interesting properties. One of the most interesting properties of the projection matrix is that if you look at PA times PA, that gives you A transpose A inverse A transpose times multiplied by this A transpose A inverse into A transpose. So, this is PA multiplying it by PA, and you can see now you have A transpose A inverse. So, these things cancel, and what you are left with is again you can see A transpose A inverse into A transpose, which is P. So, this satisfies the property PA square equals PA. In fact, PA square equals PA raised to the power of n, correct, any integer n, right, or any integer n greater than or equal to 1 is PA. So, this is the projection matrix, and this is basically the intuitive or the intuition behind the least square solution, which sheds which is basically very conducive to sort of intuitively understanding the reasoning and the methodology behind the least square solution. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.